So what I have here is a glass prism. It's got several interesting surfaces, some inclined surface, and here is a spherical indentation. So it makes a good lab to study some phenomena. So let's see what happens when I shine a laser pointer right through. Well, the beam of light simply goes through the glass. Try to get this going here. As you can see, it just shines right through. That's the spot. Now, that's not too surprising, but what if we have an inclined angle like this? Well, several things are happening at this point. You can see that a portion of the beam of light just simply reflects off the top surface, and then another portion of it gets refracted. You can see that the bending is away from the laser pointer direction. This bending or refraction of light is an important property of light. Then there's something else going on here. That refracted ray is over on this side, but there's some other ray here. That's called the internally reflected ray. So that can be explained as follows. There is one portion of the beam that's coming out in the refracted side, and another portion of the beam that's actually getting reflected off this surface and coming out. And that's called the TIR, or totally internally reflected ray. So these are all the things you can see in one single demo. That's the reflected ray, that's the refracted ray, and that's the totally internally reflected ray. So we'll be looking at some of these phenomena, and then you can study other things, including curved surfaces and prismatic surfaces with the same object. So let's first talk a little bit about light itself. As you saw in the previous videos, it's an electromagnetic wave, which means that it's got electric field and magnetic field oscillating at right angles to each other. So let's take a look at the fundamental description we have of electromagnetic radiation. The electric field oscillates in one plane. Let us say it oscillates in the XY plane. The axes are drawn a little bit funnily. The Z-axis comes out and the X and the Y-axis are in the plane of the paper. Well, I guess that's a traditional way. It's not actually funny. The B field is at 90 degrees to the electric field, and so that goes like that. And just to make this clear, I'll put some fin-like shadings. And for the electric field, these fins essentially represent the amplitude or strength of the field at any given point x. Now the picture is not static. This wave is actually moving forward, and it's moving at the speed of light. The speed of light is usually called by the symbol c, but in a medium, the speed is actually less than c, so I'll call it by the symbol v. The refractive index of an object is the ratio of the speed of light in vacuum to the speed of light in the medium. In this particular demonstration, the refractive index is something like 1.5. Most likely this paperweight is just it's a corporate paperweight. It's not made of anything fancy, so it's probably just soda glass, which is melted sand. So 1.5, I would imagine. So the speed of light would be less than 3.0. 3.0 is the speed of light in vacuum. So because the refractive index is 1.5, the speed of light in this paperweight is going to be 2.0 times 10 to the 8 meters per second. So this quantity is called the refractive index. There are substances with fantastically high refractive indices, and those are called Bose-Einstein condensates. The refractive indices of those materials is so high that light practically crawls to a stop inside them. Now, there's one concept that I need to tell you, and that is that light carries energy, and this energy is carried also at the speed of light. The way we do that is to create a new vector. So let's just take electric field vector at any point. I'll call that E. And the magnetic field vector at any point, I'll call at the same point, actually, I'll call that B. And these are both functions of space and time. For example, here it gets really small, here it gets really big, but on average, they carry energy. This energy carried is given by what's called the Poynting vector. Poynting is the name of a scientist, even though in this case, the Poynting vector also indicates the direction in which the electromagnetic radiation points. So Poynting vector S is proportional to E cross B. The exact expressions appear in the notes, and I'm not too interested in them right now. It's just the right-hand rule. E is that way and B is this way, so E cross B is in the direction of the wave propagation. So this is called the electromagnetic momentum rate. Now, if you wish to make a spacecraft which has to travel long distances, the way you would do that is to create a large interstellar sail on that spacecraft. So I'll show you a little cartoon rendition of what a future spacecraft could look like. Could look like that. And then what you do is there's a little space station and everything tethered to it, and this spacecraft sail itself is probably the size of a large United States state, and this could be a few thousand pounds. And then what you do is initially you let lasers shine on this spacecraft from the Earth, and they put their Poynting vectors on the sail, and the sail is able to go out at a certain speed and gain some acceleration and leave the planet. And then once it gets out in the deep space, you cannot keep firing these lasers, and so they have to stop at some point, and then starlight is used to make this go further. So you sail it just as you would sail in an ocean or something. You just turn the sail this way and that, depending on where the most sunlight is coming. Now, once you have the understanding that this Poynting vector carries all the energy and momentum information, you simply stop talking about the E and the B fields. So we'll call this a ray of light. A ray of light is just the abstract representation of the direction in which the Poynting vector travels. So all straight lines with arrows simply mean the direction of the Poynting vector. So once we have that understanding, let us talk about the laws of optics. The first law of optics is the law of reflection. That says if you go from a medium of refractive index n1 and a medium of refractive index n2, you're not too interested in what happens here. So let's first do the law of reflection. It says the incident ray, and remember this is the direction of the Poynting vector, when it bounces off the surface, there's another ray. So I'll call this theta 1, and I'll call this theta r. The reflected ray, theta r, and the incident ray, theta I rather, are going to be the same. So that's called the law of reflection. The second law that we saw in that demo was called the law of refraction, and this works as follows. This time you pay more attention to what happens in medium n2. So this law states the following. In the medium n1, the angle made with respect to the normal vector is always what we use here, n hat, to talk about the angles. There is also the reflected ray, but we're not going to talk about it now. We'll talk about what happens instead on this side. So if the medium n2 is more dense, so I have an example here. I have a little jar of water here, and if you notice, if I put my fountain pen, the other side of the fountain pen inside, it appears a little bit broken. I don't know if you can see this. The same thing happens with soda straws dipped in milkshakes. Well, maybe Kool-Aid, not milkshake, because it's more transparent. Let's call this theta 2, because n1 with theta 1 and n2 with theta 2. Then the law of Snell, known as Snell's law, is a statement that n1 times sine theta 1 equals n2 times sine theta 2. Snell's law is, like the law of reflection, derivable from what's called the Fermat's extremal time principle. Fermat's principle states that light travels in a path that minimizes time. In some cases it maximizes it, or the more correct way to do it is extremal principle. It can be maximum, minimum, or neither, or just a stationary point. And Fermat discovered this in the 17th century, and this is true for all behavior of light and electromagnetic radiation in general. There's also a third law of optics, which I have relegated to my notes. I won't describe it here. It just basically says if you go from one medium to the other, the frequency stays unchanged, but the wavelength compresses because the speed changes. Now let's try to use Snell's law to understand this phenomenon we saw earlier of total internal reflection. How is it possible for something to get totally internally reflected? So let's assume that you have an object, like a fish, for example. So that's my drawing of a fish. And the fish is located some depth d below the water surface. So we are in water here. The refractive index of water is approximately 4/3. The refractive index of air is almost 1. It's almost the same as vacuum. So the fish is going to put out different light rays. Light rays are going to come out, I wouldn't say come out of the fish, it gets reflected off the fish from the sunlight. So if you have a shallow ray like this, it gets refracted out according to Snell's law through a bigger angle, because it's the reverse of that. But there's going to be some point, a critical point, where this angle keeps getting bigger and bigger, and now it gets to be 90. That's called the critical angle. Well, what's called the critical angle is this one, theta sub c. So theta sub c is called the critical angle. Anything beyond the critical angle, and what's going to happen is that this ray of light that emanates from the fish is simply going to be bounced down. So from the fish's point of view, its entire world of the world outside the water is encapsulated in this cone of angle theta c. It's a three-dimensional cone, and that's called a fish eye's viewpoint. And this is the origin of the fish eye lens in camera. If you're a camera a photography expert, you know that the fish eye lens does the same thing. So how do we apply Snell's law? It's just straightforward. Let's write it down here. N1, which is this medium here, N1, that's N2, times sine of theta critical is equal to N2 times sine of 90 degrees, which is 1. So I get sine theta critical equals N2 over N1. N2 is 1 and N1 is 4/3, so that's going to be 3/4. And that gives us theta critical. Turns out to be something like 48 degrees. And if you want, you can find out the area of the conical patch that can actually be seen this way. So the area of the cone. By the way, if you're outside this cone, you cannot see the fish. The fish can see you, because the fish has to be able to see you to survive, right? It can see everything outside in this small cone, but you cannot see the fish because you're going to be outside that cone. So you have to be able to see the fish. You have to come to this inside this radius, and that's pi r squared. The radius r is related to, that's the radius r, is related to the distance d using trigonometry. So that's r over d equals tan theta, and from that you can figure out what r is, and from that you can figure out the area if you wish, and a number of other things. So that's just a simple example of applying Fermat's Snell's law in this case to something like spear fishing.